This story is about working hard even when it seems silly,
It's not boring.
and for the people trying to make crazy things happen.
It's that shot of optimism, yeah. It's not boring.
Not boring is for the optimists.
It's that
Take a little shot of optimism. Take a little shot of optimism.
it's not boring.
Let's just zoom out and take a little shot of optimism.
It's not boring.
Happy Thursday and welcome to Not Boring Founders. Last week, one of Not Boring Capital's portfolio companies, Melonfrost, announced its latest funding round in a Forbes article. The title, Brooklyn Evolution Startup Melonfrost raises $7 million to make more microbes. Melonfrost is one of the coolest, most ambitious companies I've ever come across. It's sci-fi brought to life. The company is the brainchild of Sam Levin and Lauren Amdahl Culleton, a dynamic duo of creative scientists that go way back. They've known each other since preschool. As they grew, Sam pursued some of the most fundamental questions in evolutionary biology. He earned a PhD at Oxford researching the origin of life. During that time, Lauren studied mechanical engineering and engineering physics at Stanford. Lauren worked in a variety of top research labs exploring problems ranging from the design of electromechanical systems to the development of state-of-the-art reinforcement learning algorithms. He even worked on mechatronics for The Lion King on Broadway. A few years ago, home for Christmas break and sitting at a bar, they discussed the overlap between machine learning optimization and evolutionary optimization and planted the early seeds of doing something together. When they told a third childhood friend, Luke, who was working as a project manager at a big tech company, he pushed the trio to turn it into a business. The result is Melonfrost. They're designing organisms through evolution to solve problems. They create cells to make new materials, drugs, or food ingredients by applying environmental pressures in the company's evolution reactor, guided by machine learning control algorithms. Like atomic AI, which we wrote about a couple weeks ago, it's the intersection of biotech and AI, and is an area that we're really excited about. If Melonfrost is wildly successful, we might live in a world in which we can grow anything we need. You know what? I'll let Sam explain. Please enjoy my conversation with Sam Levin, the co-founder and CEO of Melonfrost. Sam, welcome to Not Boring Founders.
Thanks, Packy. Good to be here.
So where am I catching you? And I know the answer to this question, but it's cooler than most of the people that I talk to.
You mean physically in the world where you catch me?
Physically in the world, and tell me about the space that you're in.
I'm probably no more than a couple miles from you. I'm in Brooklyn. We're in our joint lab office in Industry City. So I'm in like a soundproof pod. I've got the lab on this side. You might be able to see parts of it, or at least some plumbing, maybe.
Yeah.
If someone uses the emergency eye wash, they'll be like right there. So,
Perfect.
and then the rest of the office is over there.
All right. So most startups that I talk to don't have emergency eye wash stations. What does Melonfrost do?
We evolve microbes. Apparently, once you're playing around with microbes, you have to have things for your eyes. Yeah, where this is a BSL-1 lab, and we are evolving the next generation of microbes for therapeutics, materials, food, hopefully everything.
And when you say that we're evolving microbes, what does that mean? How did you come up with this idea? It's a wild concept when you explain it.
It is. Maybe I'll start with the how we came up with it, because it's an easy way in. And so I'm an evolutionary biologist. I grew
Me
up,
too.
and of course, I know it's how we know each other. We'll catch each other at Journal Club this week. I grew up in a small town in Western Massachusetts. I went to Oxford for my undergrad, became an evolutionary biologist there. I stayed for my PhD. Most of my work has been on the origin of life. I was working on that problem. To solve it, I was developing very general models, very general equations of evolutionary dynamics, basically predicting how things evolve. And my childhood friend, who I went to preschool with, grew up with my whole life, also from the same small town in Western Massachusetts, he had gone to Stanford and become an engineer and computer scientist. He was working on reinforcement learning research, machine learning optimization, and we began talking about this idea of essentially combining our two fields, using machine learning to fill in the gaps, evolutionary dynamics equations, to learn evolution and learn it well enough to ultimately predict it and control it. And so that's how we got into it.
How did that conversation kind of start or happen specifically? Like, first, I want you to go back and tell us about your town and like how big your class was and
Right.
the rest of them at Ivy League schools and fine UK educational establishments? Or tell me about your relationship and then like how it came together. Did you just really want to work together? And so you like figured out a way to work together, or did the conversation evolve, no pun intended, in a different way? Like, where did that come from?
Good luck not using evolve over and over again in this conversation.
No,
I've
I'm gonna
found
use it 100.
I have to avoid using it figuratively all the time because I also use it literally all the time. So yeah, the context is maybe useful. We grew up in a very small town. We actually grew up in adjacent towns. Mine, his was the big town. It's 5,000 people. My town is 1,200. It's very rural. All of the local towns pool to one high school. The class size is 100 kids, but we actually worked together in high school. We started this farm at our public school in Western Massachusetts, which grew food for the cafeterias in the school district, served as like an educational resource for kids, et cetera. And it was like a student run farm. So we had actually experienced working together on, at the time, what felt like a really big project, right? We had a budget of $100,000 a year. We were growing a 2-acre farm. We were distributing food. Anyway, so we had worked together, but then we went our separate ways. We were a million miles away. I was in England. He was in California. And those very early conversations started completely academically. The one specific memory I have is being back at a bar or restaurant in our hometown on like a Christmas break and looking at each other's work and noticing similarities in the maths between machine learning optimization and evolutionary optimization. So it started as this seed of there's something here, there's something interesting going on here. And then we pursued it further and further, not thinking about it as a company, but obviously also deep down having a history of trying to change things together and build things together and make a difference and stuff. So those two threads, this very, hey, wouldn't it be cool if you could learn evolutionary dynamics and publish a paper about it? And we've built things together. We know how to work together and stuff. And then finally, third friend, this is where it starts to get ridiculous. Warren, our other friend, who we also went to grade school with at the time, was working in industry, working at a big tech company in project management. I think he was the one who really helped us start thinking about it as a business. And we had known each other all for 25 years or whatever. So that's how it came together.
Unbelievable. What's it been like working with your two friends now, like in a more professional, high stress environment?
Warned us against it, right? Like when we were raising
Yeah.
our first round, everyone was like, this is a terrible idea. You shouldn't start saying to friends, like you'll hate each other. And we hate each other. It's been amazing. We really had insult to injury, but in fact that we also live together.
Amazing.
So we spend obviously all our time together, but I think it's actually become one of the greatest strengths of our company and greatest assets. We know each other incredibly. We trust each other to the ends of the world, and we're counterweights to each other. We have different worldviews. We have different ways of thinking about things. We have different strengths, and that's created a really strong foundation for building a company. And I think a really strong emphasis on relationships and people for building out a team. So
Yeah, it's interesting because there's obviously different skill sets and different worldviews and all those things that you bring, but you're also nerdy enough to be sitting in a bar/restaurant over Christmas break, like comparing your academic work. So aside from, I guess, that curiosity, what are the things that you have in common that that drive the ability to work?
I think we are all very ambitious in the sense that when we see a way something could be, whether that was we could be growing food for the high schools in our local area, or we could be growing all of the world's resources in our lab. We are very good at just committing to that path and doing whatever it takes. I think Lauren and I certainly are both very cerebral and love solving problems and thinking deeply about things. And we love each other. We love working together. We love spending time with each other. So that's part of it. And I think I mentioned like the trust thing. You know, I can't imagine trusting anyone as much as I do them. And
Yeah.
when the amount of risks you take when building a company, like, this, I can't think of many more things more valuable than being able to like trust the person next to you with your life and know that they have your back in every way, will help you through any like tough times, something we have in common.
So going back into your background, I remember talking about the fact that you discovered aliens. So you were studying the origin of life, you discovered aliens. Can you tell us that story?
Sure. Yes. I am former astrobiologist turned evolutionary biologist turned evolutionary peddler or something. But, yeah, so when I mean, part of my work was like the reason this all came about is we can't see what happened at the start of life, right? We don't, there's no fossil record from the beginning. So we had to use equations to try to predict things, which meant developing these general equations to predict how things evolve, even in the absence of specific knowledge about their biochemistries. And at some point, it occurred to me that could mean something for making predictions, not just on Earth, but in other places, like other planets. And another colleague and my supervisor during my PhD were like, hey, let's like write a paper to maybe kick off some ideas here. We wrote this paper called Darwin's Aliens, about how you could use evolutionary theory to make predictions about life on other planets. And what felt surprising at the time, but now in retrospect, shouldn't have been surprising. It got picked up by the news. It became like Oxford scientists claim they know what aliens look like or something. And so it really, it got a life of its own.
Yeah, in retrospect, it's a great name too, Darwin's Aliens. So I think
I know.
the Oxford thing plus
really
that,
screwed myself there.
you really did. I guess the question, other than the fact that it's an interesting story, the reason that I asked is because that part of your career or your academic life was looking backwards at the very beginning, and now you're looking forwards and figuring out how you evolve microbes and evolve organisms. What differences are there? Like, how much can you take the equations that you came up with looking backwards and apply them looking forwards? How different is it? What, I guess, translate that for me.
Yeah. One thing to say there first is I think a lot of that is Lauren's influence just on a fundamental level. Like I have always been someone who wants to understand why things are the way they are and tease them apart. And I have rarely met anyone in my life who has as big a vision and as creative an imaginary vision as Lauren. He can see a million miles into the future. And so I have learned a lot from him about how to think that way. And he's a major influence in that. So I think at its core, right, the whole idea here is one of the wonderful things about natural selection is it is this algorithmic process. It's an algorithm. It's the oldest algorithm there is and probably the best. It's what made you and me and our brains and everything around us. But it is an algorithm. And so you can get down into the weeds of the chemistries and the biology, but you can also abstract it and predict a lot in the absence of specific information because it is an algorithmic process. And that means we can use it to make predictions about things that happened 4 billion years ago and 4 billion light years away and 3 weeks from now in our evolution reactor in the lab. So that's like one of the core tenets of what we do.
So I guess it's a good time to dive back into what exactly it is that you do, because just in case people can't piece together all the pieces from evolving microbes, what happens at Melonfrost? Take us from the very, very beginning when you talk to a potential customer to like what the whole process looks like.
Yeah. So I should say really what we're doing is like creating new microbes. And we're doing that for the purpose of solving problems, whether that's creating a cell to make an alternative food ingredient or a drug or a material. That's what we're doing. We just happen to do it by steering evolution. At the highest level, what happens is a customer sends us a strain or a cell or a cell line and a goal. Make more of protein X or make this cell grow faster or whatever, some kind of goal for the organism. And then we do some stuff in the lab and then we send it back. And the stuff in the lab is obviously the heart of our technology. And our technological platform has two parts, software and hardware. The software is a collection of algorithms, machine learning control algorithms, which take in data and send out instructions. They are what's learning how organisms evolve and deciding how to change how they evolve to evolve them to what we want them to do. That software is connected to our machine that we created, which we call the evolution reactor. In that machine, we grow hundreds of populations of cells in parallel. We independently control and measure each one. And that machine streams all that data. The algorithms are learning how the organisms are evolving, sending instructions back down to make changes. And that's a closed loop where we set a goal in the software, maximum protein expression, and that platform runs automatically, continuously until that goal's met.
So someone who wants an organism today, like how do they get it before Melonfrost existed?
So the entire sort of field of symbio has been built around what genetic engineering. what I call rational design. The idea there was we want organisms to have new traits. We want them to make a drug or food product or whatever. How do traits come about? They come about from DNA. If we can read and edit DNA, then we can change their traits by changing their DNA. So that's, people have heard of CRISPR. That's like the buzzword. There are other ways that is where you go in and you tinker with genes to get new traits. And that has what's been done for the last 20 years, even longer. I think it started with Genentech making insulin in bacteria. That's great. And we've solved a lot of problems that way, and we've come a long way. But ultimately, it is very expensive, time consuming, slow. It's a manual guess and check approach because we don't know really how genes arise to traits. What we care about is traits. And we have no way to actually sit down and write A, C, G, C, T and get more protein or a new drug. So what people do is they brute force this approach where they try every single possible genetic change and see which ones do what, and then try to get it to stick. And this is achieved by armies of brilliant PhD scientists pipetting, sometimes armies of robots doing that. But it takes a lot of time, it takes a lot of money, and often the changes made don't stick. And that's really where Melonfrost stands, is we think that's not going to get us the future we believe in, not fast enough. But we're lucky because there is something that is really good at changing genes and knowing what the right genes are to change. And it does it for free. And it's been doing it for 4 billion years. All we need to do is put a steering wheel on it. That's obviously evolution. So we put a steering wheel on evolution. The idea is we offload a lot of the labor that's normally achieved by hundreds of PhD scientists and robots. We offload that onto the natural process of evolution.
So what does that evolutionary process look like in these compressed timescales? Because I would imagine your customers don't want to wait billions of years to evolve the perfect organism. Like specifically, like how are you applying different pressures on the organisms? Are some dying off and some reproducing? And is it like you'd picture when you think of evolution?
Yeah. I think one way to think about what we're doing is speeding up the process of evolution. And so you don't have to wait billions of years. You can get it in a few months when you need it for your product. But at its core, yes, it is just evolution. So we're running hundreds of evolution experiments in parallel. In each one of these chambers, there's a population. The cells are competing with each other. Some are dying off, some are surviving. There are mutations arising. Some of those mutations lead to an improved trait from our perspective, more of your product, let's say. And what we are doing is we are changing the conditions in each one of these chambers so that the fitness landscapes change, so that the mutations we want sweep through the population. And we're just doing this at a massive scale and powering it with machine learning so that search is efficient, so that we can achieve it in months in our millennia.
And are you waiting for the right mutation to show up and then leaning in, or can you direct towards a particular mutation ahead of time?
No, mutations are random. They will always be random. We can increase the mutation rate if things aren't happening quick enough. But fortunately, every position in every cell is mutated every generation across the whole population. So we're getting every mutation we need. We just have to find the ones that we want. And since it's random, selection is directed, and we're using that part to get the mutations we want.
So everyone's gotten familiar with machine learning and AI in the past kind of couple of weeks. I hired somebody off of Replit to try to train GPT-3 or fine tune GPT-3 on some of my writing. And it's like, even that, he's having some trouble figuring out exactly how to do, maybe there's not enough good writing. All to say, it feels 100 times harder to figure out how to train the models and the algorithms originally to evolve microbes. What did that original process look like before you had the evolutionary reactors? What was the initial starting point on the ML side?
Yeah, I should clarify too that we're using very different kinds of ML approaches than the kinds used to train.
This is not a large language model.
Yeah, weirdly not a large language model.
Yeah.
And Lauren's background was very much in these search problems where you aren't dealing with data sets that are large enough to do this kind of more traditional deep learning. And that's where I think a lot of our secret sauce is. And a lot of where we started before we were even thinking of it as a company is there's this search space. It's large, but the data set's small. how do we search efficiently through this? And how can we use like some of the more advanced and novel ML or RL approaches to do this? So that's one thing that it's like a very different approach to ML than when we're like chatting to GPT. But otherwise, before we had the evolution reactor, we started with simulations. The good thing is we know how to simulate a naturally evolving population. Like I did in my PhD, it's how a lot of evolutionary biology is done. And that gives you the right sort of structure. The hard part at the beginning is like, how do you frame this problem? How do you frame the problem of an evolutionary search so that it's amenable to RL or ML approaches? So the simulations help give you like the right structure for the biological problem. They give you like initial data sets trained. And then we actually just like with our pre-seed round, we got a couple of bioreactors, just like off the shelf bioreactors to actually like test that against the real world. The problem is a bioreactor costs $40,000 to $60,000 and we wanted hundreds or thousands of them. So we had to build our own. That's how the evolution reactor came about.
What was that process of building the evolution reactor? I mean, I know you
Wild.
mentioned it's like the littlest things too that will hold you up. Tell us about building hardware on top of all the crazy stuff that you're doing.
I know it's really, we just had some new people join the team. And I think it is, if you're coming from like any kind of more traditional company, it's pretty wild to jump into a company that is doing like cutting edge biology, cutting edge ML data science, building our own very innovative hardware, building a software platform to connect. There's a lot of different strands going on. And definitely at times it's been a lot to handle. But hardware in particular is just, we have our like tagline on our Monday board. We use Monday to track some of our work, and each of the different like pages have little taglines, and the one for is hard. Yeah, like it's hard. And yeah, exactly. Like you can have just cracked a novel sensor for detecting multi-wavelength fluorescence, and then your gaskets are all busting or something, like some problem that would like affect like a high school project. There's so many parts to it. And sometimes it's like the simplest things that you overlook that get in the way, and you have to deal with lead times, and it's just messier than software, obviously.
So a lot of brain power, a lot of sweat, blood, and tears have gone into getting us here. You mentioned this like big vision that you want to see in the world and that the current kind of system won't get there fast enough. What is that big vision? What are the kind of things that you're making now? And then what do you think the kind of things that you'll be able to make are in the future?
The big vision is like pretty simple. We want to grow the world's resources in cells. That's it. Not 100% of them, 50% of them, something like that. So that's the big vision. There's a long way to go to get there, obviously. I think really that boils down to we fundamentally believe that the future won't be synthesized, it won't be engineered, it won't be manufactured, it will be grown. And specifically, it'll be evolved. So that's our vision. Right now, we are evolving and optimizing strains in our evolution reactor. We optimize the strains, we optimize the conditions under which they're grown. And we do that for other people. Eventually, we have to expand the capabilities so that we can modify more and more traits and work with more and more organisms. We have to move beyond just microbes into mammalian cells so that we can tackle therapeutics. And that requires expanding our hardware capabilities. We're expanding our software capabilities so that there's more ability to interact with this anywhere over the cloud and on the web and build out our UI, eventually put that in the hands of customers. And then we have to we have a very big vision for how we can translate that into manufacturing and production, by which I mean manufacturing production in cells. So that has to be built out so that we can not just improve and optimize the strains and process conditions, but actually directly manufacture them efficiently.
And it's a vision that I've gotten more and more excited about as I've gotten to work with Elliot Hirschberg on our team. And I feel like every piece that I read of his, he writes something about the fact that everything should just be grown on trees as opposed to us building it.
Yeah.
When you say 100% or 50% of the world's resources, take us to that world 100 years in the future or whatever. Like, what are the things getting in the way of that right now? If I wanted to say like, I want a lunch right now and I want a burger and a soda and whatever. I don't know if that's the right example to use, but if we're talking 100%, then it's everything. What's in the way of that happening right now?
So there is building. So actually getting cells to make all the things we want them to make, that's the one we've made the most progress on. We've figured out how to put a jellyfish gene in a E. coli or whatever. Like we're getting there. That like initial build has made a lot of progress. There is a lot of optimization to be done because often what happens is we like pull a gene from one place and put it in and it works at first and then it doesn't, or it's toxic to the cells. A lot of optimization to be done on the build. That's where we're starting. And then there is the scale, doing this like at an industrial scale. Is a sort of graveyard of companies and projects behind us of people who like got a cell to do something initially, but then couldn't actually get it to make 100,000 liters of its product. And that's where I think evolution is uniquely poised to solve that problem. Has a very good track record of making robust solutions. We're here. We're having this conversation, but that there are other work has to be done, not just Melonfrost. We have to build new tools, infrastructure for actually being able to produce these cellular, microbial, biological products at a global industrial scale. And it's been done in some instances. We know it can happen, but there's a lot of like biological optimization work and a lot of like hardware optimization work to make that as efficient as it needs to be. And I think ultimately it's going to come with very fundamental changes to, and Elliot obviously has talked about this, but fundamental changes in what manufacturing looks like. I think I see sometimes, right? And obviously I can be a dreamer, but I see these companies who have got a microbe to make drug for like cancer, let's say. So they've like done some incredible thing, or the microbes making a burger, right? And then like I look at how it's being manufactured and it looks like an oil refinery, right? It's like some giant place in Alaska that's like growing the microbes. And to me, it just doesn't seem right about that, right? That's to me like, that's not bold enough. If we're doing this, we're hacking cells to grow our plastics and concrete, then one of the values there is like cells carry their information with them everywhere they go. And so we should be able to be manufacturing your burger and your soda in the room with you. And if not that, it should at least be done down the road at like the local cellular manufacturing facility. I think that's part of that vision. And obviously that requires major changes and it's step by step, but like, obviously we should have a bold vision.
But there's nothing that you can see on that path that's like physically impossible. You think it'll happen. It's just a matter of maybe a very long time.
Look, again, I can sound like a broken record, right? But biology made your brain, like, which made everything else. Like, it made trees, it made like, we already get everything from biology pretty much. There's some exceptions. And of course, there will always be exceptions. I don't really mean 100%. I just mean everything that can be should be. And I think the can be is a much bigger bucket than we currently think. So, yeah, DNA is an unlimited language, right? It has no limit to what it can produce. You just keep adding letters and you can keep increasing complexity. I don't think there's like a physical blockage. I think there is some serious technological development. And I think we're helping with that, but I think other people are too. And it'll be a road and it'll have its dips and it'll have its disasters, but we'll get there.
What sorts of products might your organisms go into today in the next, like this next year? What are the categories that people should be thinking about?
Yeah. So the thing we're working on right now is in the food space, an alternative food product. That means we don't need to cut down rainforests or industrially farmed cows to get some of the ingredients in our food. So that's the specific things there right now. But we're in conversation on some exciting like chemicals and materials products. So things like plastics or chemicals for water treatment, those kinds of things. And looking a little further out, we're talking about energy, we're talking about drugs, therapeutics, and some other sort of more maybe flashy materials like alternative textiles, like that kind of stuff.
Yeah. So even in the near future, it's not particularly limited to in what you can design.
That's the other, and one of the things I think is cool about this approach is, again, traditionally when you engineered things using genetic engineering, there was a tremendous amount of expertise is needed to change like a single pathway. You do a PhD, you do a postdoc, you do another few years, and then you like understand the metabolic pathway in this one species that makes this one thing. And so when a company wanted to start a new project, they need 35 scientists to like work on that. we jump week to week between yeast, bacteria, between lipids, proteins, between growth rate, expression. It truly is general because we're not doing the work. We're loading the machine. We're like, we did the upfront work, but then everything else is automated and the actual algorithms are very general. I think that is very new to this field, is that ability to jump between organisms, trade, sectors, industries, products.
It's cool. It makes me think that despite how unbelievably hard, like you could give me a billion lifetimes that I'd never figure out how to do this, the stuff that you're doing on the technical side is maybe the limiting factor in what you can do in the short term is actually just go to market stuff. Do you want to have you or a sales team focused on 75 different industries, or do you want to get
Yeah,
really deep in one? Like, how do
no,
you think about
totally.
that trade off?
I think right now we are learning about that trade-off, right? So right now we're like having conversations with everyone, figuring out who the right first partners are. And we are partly assuming that we will learn about these industries and these organisms and these traits and these problems by some of these early like pilot engagements and figure out whether from a sort of business go to market perspective, we can stay broad or we should pick one of these to focus on. And I think that's a decision we'll be having to make over the next few months to a year, is how much to focus in the beginning from just like a business strategy perspective
Yeah.
of needing to get to know an industry and a sector and how the language, like I now have a conversation like one week with a pharma company and one week with a food company, and like the language is just totally different for the same ultimately biological thing.
Yeah. The reason I'd be about entrepreneurs, because what's coming to my head right now is there a way to use the evolution algorithm to message a bunch of different industries and have it figure out what the right industries and right approach for each industry is, so you're not limited there either? I'm sure we'll get there at some point where like this salesperson's expertise in an industry is no longer required and you can switch from industry to industry. But that's why I'm interviewing you on a podcast and not building this company. What does the business model look like today and where is it going? Like when someone says, I want this organism, like what happens?
It's really straightforward right now. They want an organism, they want to solve a goal, and they pay us some money. Like we've purposely made this like at least to start like a pretty simple fee for service model. And I think it's new that we're able to do that because we have built a low cost, low input way to modify strains. I think ultimately the thing we're building here that's really valuable is the world's largest evolutionary data set. And I think there are a lot of ways that business model, here we go, can evolve. But I think the most important thing we need to do right now is work with different kinds of customers on different kinds of organisms on different kinds of traits and begin building our set of trained models and our data set of evolutionary data and begin learning these sectors and industries, many of which themselves are young and changing week to week, month to month. And so we do something really well that no one else can do right now. Let's get paid to do that and keep some cash flow going. We learn what the best way to like capture value over the long term is.
Yeah, it's interesting. I feel as Elliot's kind of taken me down the biotech rabbit hole a little bit. There seems to be a lot of companies that start with some sort of like working with pharma and licensing something, and then they want to own as much of the development process as they can and bring a drug to market themselves and all of that. I know the one way you could go is using that data set and going the software route. Does part of you think the opportunity is a quarter of the stuff made in the world that you should vertically integrate and just be like the biggest company and make everything? Like, is that
Of
even?
course.
Yeah.
Of course. Yeah, of course. And like, I think there, we've seen examples in this space of people trying that and failing, of people not doing that and possibly failing because they didn't do it. I do think there is a huge potential to like have a major impact by finding the verticals that we are best poised to tackle, because either they're totally intractable through other methods and evolution is the way to do it, or we've just built a massive data set around this, or the reasons you might imagine, and that we can both have a huge impact and capture a lot of value by doing that. I think the really important thing and the mistake we don't want to make is we want to make sure we are ready when we do that, because it is expensive. It is risky to build out a vertical. And we have some, I think our goal here is if we go after verticals that we've built our data set and our like internal expertise and sort of process expertise to the point where we're like we are 100% sure this is the one to go after first, and we're going to do that and that's perfectly well on it. Yes, I obviously vertical is always an option.
How many hours a week are you guys working right now?
I don't know. it's it's obviously hard. Like we always joke to each other, like, how come no one told us how hard it would be to start a company? Which isn't true. People do tell you, but you just can't believe them. You can't understand how hard it is until you've done it. Or I feel that way at least. So it's very hard, but we also all value not being burnt out, being like clear headed and rested and all of that stuff. And we really value that for our team and our and employees and stuff. So I don't think we're killing ourselves, but it's hard.
No, for sure. Yeah. Obviously there's the normal startup thing, but then you just think about the size and scale and scope of the opportunity here. And it's like, I could sleep or we can go do this other thing.
Yeah,
And yeah. And
exactly. And that's Lauren really he wears so many technical hats in terms of uh, engineering, mechanical engineering, electro engineering, ML, data science, software engineering. I haven't even talked about the software platform we built. He's carrying a lot of that mental weight. But again, it's a benefit of having each other as founders. And we have an incredible team here and it continues to grow. And that's lifted some of that burden from our shoulders. So
how big is the team now?
we are 13. It's a
Amazing.
great number.
Yeah. The fun. Anything up to like 30 is really fun.
Someone just pointed out, we just crossed the threshold where we don't like necessarily all fit around a table at a bar. I think Sean said that. And I was like, you know what? That's true. That is like an inflection point, right? Like we're not guaranteed to all be like around a table talking. So we have to exert extra effort to make sure that there's like a consistent flow of communication.
When you
That
guys go
worked
to the
or at
bar, this is really in the weeds. When you go to the bar in Industry City, do you go like inside the buildings? Do you ever leave those buildings? Is there a spot that is like the Melonfrost team spot?
We don't even leave the lab. We all sleep there. No, we do go to the bars at Industry City, but we also, there's like other bars in the neighborhood that we got. There's a place called Minis. There's a place called Mama Tried. So we like make an effort actually to get out into the real world a little bit because you can get lost in like it's like Industry City metaverse. Yeah. And there's a lot of bars. You should go to a different one every night of the month or something. Go get out.
All right. Yeah.
You'll have to come meet us.
I really do need to get over there. Tell us about the software platform before I let you go and ask crazy questions at the end. Tell us a little bit about the software platform that you just alluded to.
Yeah. So I feel like it's maybe the part that is easily gets overlooked because we're an ML and an evolutionary biology company. The evolution reactor is flashy and ML is just like inherently flashy. But the glue between the algorithms and the hardware, the evolution reactor, is this, I think, pretty impressive software platform because there's a tremendous amount of data, varied guides being streamed from the evolution reactor. And then all of these instructions that go back down in real time. So we built out this platform that at its core is a data pipeline that glues together the algorithms and the hardware and actually make it a closed loop system. But there's also like a basic UI and on the web browser, it's hosted in the cloud, which we use to monitor the runs and visualize all the biology and stuff. I think is also the beginning of what could be a UI for customers and other people. And I think part of our like broader vision, not just for Melonfrost and our role, but for this industry and ecosystem is that there will be more and more tools that make this less and less like manual pipetting at lab benches and more of like an automated software-esque industry where things are plug and play and they are like abstracted into boxes and stuff. And so I think that is important that we have that element and that platform gives us the beginnings of UI and stuff for our machines.
Elliot had to say, talked about this box that just pulls atoms from the air. I would imagine we're probably a fair way away from that, but you could imagine a world here where like you send customers like the raw beginning materials and then they use the software platform and maybe an evolutionary reactor and just do it themselves.
That is exactly our vision. So what the evolutionary trajectories that we learn and our learning brain thing, the evolution reactor, can be sent down anywhere in the world. So when we want to actually get into manufacturing these cells for people, that's exactly how we envision doing it, is having reactors and like replicas of our evolution reactor in different places and just sending those instructions all over the world and creating new strains where they are needed.
Do I have to ask an ethical what could go wrong question here when it's all distributed to the
Probably.
edge? Or yeah, what could go wrong here and how are you preventing against that?
One of the first pitches I ever made for this company, like the first first comment I got was, "This is like Jurassic Park."
Yeah.
Which doesn't end well. No, I do think it's true for any new technology, right? Like you have to be thinking, or you should be thinking about the consequences, right? With great power comes great responsibility, right?
Spider-Man.
That's Spider-Man there. And yeah, exactly. A New York era. And it's especially true because I believe that biology is very powerful and has the power to solve many of our most pressing problems, but that means it also has the power to do harm. And so I think there are a few of us in this industry already talking about how to get ahead of that and make sure there are controls and guardrails as best as possible to make sure that not anyone can spin up a pathogen. And that's we are advantaged here in that we are not shipping a box and handing over the tools. Like we host our algorithms here. We will always keep those protected. We host our learning unit here. If we put things out into the world, it will be like an arm of the brain, but there is work to be done. And I hope and assume that there are discussions happening at higher levels than me about how to regulate this.
Do you see a world in which there could be like a stability AI to your open AI where someone's screw it, we're just doing this, but we're open sourcing everything. Good luck, people. Let's see what happens.
Wait, can you explain that analogy?
So OpenAI,
I see that. Yeah.
they control access to all of
Mhm.
their models, whereas Stability AI, which is stable diffusion, is just cool. It's all open source. Go make an Africa version.
Right.
Go make an India version. Whatever. Like,
Right.
it's all open source. And so I love that as someone who loves just like innovation and people being able to build on top of these things. And there's also pushback that says now you can unlock the model and do all sorts of things with it. And so do you see like someone less ethical or even not less ethical, just more down with open coming in and building open source evolutionary models here?
Look, see, it's already happened with CRISPR, right? So we are in many ways the next generation of CRISPR, a new way to modify an strains. If CRISPR came out, it's only Berkeley has the license to it.
The headline of this one,
And
by the
now-
way, is going to be like Melonfrost kills CRISPR. CRISPR's dead. Long live Melonfrost.
Sure. Okay. But that's your quote, not mine. Yeah. But that sounds about right. So that's what people have made like essentially functional equivalents, or it seems like the large tail of CRISPR that they've open source. I think that's essentially what this company Scriptus are. So it would be foolish of me to say that can never happen. I think we have obviously filed for patents on our specific methodology for how we do this. But of course, there's always a possibility.
Yeah.
I think one thing that's special, like that is especially unique here is we have right now the only hardware generating sufficient phenotypic data to use the only algorithms that know how to learn exterior evolution. There is this tie between the two, or this like lock that makes either one very hard to replicate on its own in any like useful, meaningful way.
So I already asked you the kind of ending question about what the world looks like in 10 years, and you gave as big an answer as you possibly, or in 100 years, as big an answer as you possibly could. But what changes in that world? So like when you get excited about that vision of making everything, like what's the world that you're picturing in your head look like? What are the second and third order effects?
Let me start with one very like academic, non-company thing that excites me is we will have learned evolution. There is a part of me, in addition to everything else we do, that had this, like, I'm an evolution biologist. I love evolution. I've loved it since I was 5 years old. And that is like part of this vision is we will have learned how to predict it. And so that's turned it into predictive science in that way. So that's something to me, like the big appeal or one of the big appeals of growing whatever percent of our world's resources in cells is that they are incredibly efficient factories, far more efficient than anything we've made. And so it is a potentially major solution to sustainability, right? Like to efficiently producing the goods and resources that we need. A very big part of this is creating a sustainable future. So that's something that will have changed. I think there is a side of this that we haven't touched on that much, which is that cells have potential to make therapeutics that are very hard to synthesize because they are fairly complex. So like when we start getting into things like antibodies, which I think we'll all become more familiar with in the last few years, like those are big complex molecules that are like hard to make synthetically. And like there's this vision that if we can really like harness and control and hijack cells, we can make a whole new class of therapeutics that will treat disease. So I know these are like big things, but I really do believe biology like is going to help solve like climate change and disease and hunger. Like it's actually how big I think the scope can and should be for anyone working in this field.
God, I'm so torn right now because that's an incredible place to end. But at the same time, like I have one specific question on the therapeutic side, which is the FDA, and this isn't like a pick on the FDA conversation, this is just a pure curiosity thing. Are they set up to approve drugs that were evolved?
I don't think so. I think there's going to have to be a lot of work to figure out how to think of rapidly evolved cells
Cool.
because right now are classified as GMO, but it's just as powerful approach as you can change them just as much. So I think that's a big open question for everyone. And I think more broadly, like on the therapeutic side, we are going to need new structures in place for the new kinds of living medicines and stuff that various people around the world are actively working on.
It's unbelievable. Sorry. So we're going to fix climate, health, manufacturing. And it's like, this is why I got so excited and why we invested and like why I have so much fun with this. Cause it is just among, if not the biggest kind of vision that we've come across. And I'm super excited by it. How do people get involved? Like, where should they find you? Are you hiring right now? The website's beautiful, actually. You should go check that out. Tell people where they can find you and what they can do to help.
Yeah, I think the website is a great place to start. If nothing else, Lauren, who is the design visionary behind that, will be happy for
Did
people
he
to look
actually
at it.
design that too?
He did all of the design work for it. Like any of the graphics or images or color palettes, all of that's him. It was like, implemented by someone else, but yes, he does all of our
Amazing.
design. He designed our space. He is many talents. So that's one place. Like we are obviously always looking for brilliant people who want to come solve the hardest problems. I think we have the general contact careers page on the website. And we're also looking for people to use our platform. So we're looking for early customers and partners who have a strain and a problem they need solved. And if anyone listening fits that category, they should reach out.
Amazing. That's melonfrost.com. Sam, thank you so much for this conversation. This has been a ton of fun and can't wait to get out to Industry City and hang out soon.
Yes, we'll take you to a bar that isn't in Industry City.
I'm coming out to Industry City. I want to go to a bar that's in Industry City.
We'll take you to a bar in Industry City. Yeah. Thanks, Packy. It's great to talk to you.